Good morning, everyone. Good morning, good afternoon, good evening. This is John Morgan. I'm the marketing manager here at AMETEK TMC. Welcome to our webinar, Floor Vibration, Fundamentals and Control for Ultra Precision and High Resolution Instruments. I'm going to go over a little bit of housekeeping, and then I'll turn it over to Mike. We have lots of people on the line, so everybody is muted right now. We're hoping that the presentation is about 50 minutes, so we'll leave, 5 to 10 minutes at the end for questions. We really want to get questions. So if you go over to your panel on the right, you'll see a drop down that says questions. Please type them in there, and then at the end of the presentation, I will read the questions to Mike, and he will answer them. So without further ado, I'm going to turn it over to Mike Georgalis, who's our Manager of Business Development. Mike?
Thanks, John. Good morning, good afternoon, good evening, everybody. My name is Mike Georgalis. I head up sales for active products here at TMC. And a little bit about myself, I have a background in physics. I've been working with TMC and vibration control for about 8 years. And prior to this, I was involved in the LED lighting industry where I did some optics and fixture design, things of that nature, in some of the early days of white light LED. Thank you for joining today. Today's presentation is entitled Floor Vibration, Fundamentals and Control for Ultra Precision and High Resolution Instruments. On today's agenda, we're going to start by talking about what an ultra precision instrument is and the problems that we see in them caused by floor vibration. So we're going to identify some of the instruments and some of the tools that you're going to see out there that are going to be highly sensitive to floor vibration, and go over some examples of what you're going to see in their image or in their resolution due to vibration issues. Once we figure out the types of instruments that we're talking about here and who's going to be interested in floor vibration, we're then going to start digging into, well, what are we dealing with? What are the sources of vibration, and where does floor vibration come from? And we'll talk a little bit about, well, how do I know if it's floor vibration or if it's something else? And so there's other sources of vibration out there that we should be aware of. But we're going to focus the rest of our presentation on floor vibration, which will bring us to our next topic, which will be characterization and measurement. So when we think we have a vibrating floor, how do we measure it? What do we use to measure it? And what does that data look like? And how do we start thinking about that data? And our last topic will be mitigation. So we've identified that we have a vibration source and we have a tool that's sensitive to vibration. We've measured it. And the final question will be, well, what do we do to get rid of it? I'm going to start today talking about ultra precision instruments. And I want to begin with a quote from Nikola Tesla. It's one of my favorite quotes. If you'll indulge me for a moment, I'll read it word for word, but I promise the rest of the presentation will not be me reading from slides. And in 1926, Nikola Tesla said, "When wireless is perfectly applied, the whole Earth will be converted into a huge brain, which in fact it is, all things being particles of a real and rhythmic whole. We shall be able to communicate with one another instantly, irrespective of distance. Not only this, but through television and telephony, we shall see and hear one another as perfectly as though we were face to face, despite intervening distances of thousands of miles, and the instruments through which we shall be able to do this will be amazingly simple compared with our present telephone. A man will be able to carry one in his vest pocket." I think that quote is a great segue into ultra precision technologies, because one of the most important ultra precision technologies that we deal with every day are things like semiconductors. And semiconductors, as we know, are use tiny features. And I won't go directly into semiconductors, but what I do want to talk about is, what do we mean when we talk about ultra precision and tolerances over time? So as time goes by, if you look at the chart on the right, we see a general trend in what we call normal size features, precision features, and ultra precision features. And the tolerances of these features decrease as time goes on. And we see this very, very evidently in the semiconductor industry, where our telephones and everyday objects we use nowadays may have taken rooms and rooms and rooms of processing power and supercomputers to perform the operations that they can do nowadays. So we're seeing this this trend towards smaller and faster. And this trend is sort of natural for all industries. For example, automobile components, tolerances for pistons and gears and injection molded parts in the 70s and 50s and 30s were much larger and much more loose than they are nowadays. When we consider that a normal type, example of a tolerance. Precision are things like integrated circuits, your semiconductors, your several nanometer type node widths and things like that. And then when we talk about ultra precision, we talk about tiny features such as single molecule biophysics, and some folks that are doing like cryo-electron microscopy who are doing angstrom type resolution in some cases. And to get you a sense of the scale as to how small these types of features are, think about a satellite. And you're in a satellite and you're trying to resolve an ant on the island of Manhattan. That's a great example I heard over the years from the semiconductor industry when talking about the size of defects that we're looking for when companies like Samsung and TSMC are looking at tiny features that can cause problems with semiconductors. And on the left-hand side here is Moore's law, which is coined for Gordon Moore, the co-founder of Fairchild Semiconductor and co-founder of Intel in 1965. And we're looking at semiconductor node sizes in the 70s where we're 10 microns, and we're looking at thousands of transistors per unit area. But nowadays, we've got our leading companies like Intel and TSMC talking about 5 and 3 nanometer nodes. We're talking about tens of billions of transistors per unit area. So as you can see, the takeaway is ultra precision is a trend over time, and things get tighter and tighter. We're always trying to look at things smaller and smaller. As a result, vibration becomes more and more of a problem, and we'll talk about that a little bit later. Another great example is, think of a human hair. If you take a human hair, that's roughly on the micron. It's on the millimeter level. If you section that 10 times, you're going to be looking at the micron level. You section it 10,000 times lengthwise, you're going to be talking about the nano level. And these are extremely tiny features. The types of instruments that we use to look at these features are commercially available, and there's myriad of companies around the world that make these types of tools and instruments. And when we talk about these, we're talking about the nanotech and nanofab space, like electron microscopy and diamond turning. We see ultra precision in the photonic space, where we're talking about petawatt lasers and holography, and even virtual reality nowadays is starting to get into a space where we're looking at ultra precision photonics applications. Advanced microscopy, atomic force microscopy, scanning probe microscopy, even a fair amount of optical microscopy, like confocal, multiphoton, and single photon microscopy. And of course, semiconductor industry, where we look at wafer inspection and surface metrology and failure analysis, and these important and defect and repair and defect and review. And so, what do we see when we see vibration problems? Well, here's a couple scanning electron microscope images. And this is at a magnification of roughly 3,000 to 5,000 times. And when you're using a scanning electron microscope and you've got a vibrating floor and it's having problems, you're going to see these waves in the images. And that's a very telltale sign of floor vibration. It could be caused by other things, but this is a very, very common vibration problem, like magnetic fields. And I have a magnetic field example as well, but we won't talk about these being electron tools. They are also affected by magnetic fields, but we won't talk about that in this presentation. Here's another example where we're resolving features at the of this sample, where we see our waves. And here's a really great example of an attempt to create a lithography pattern at 45 nanometers, where the floor vibration was so bad you couldn't even resolve a line at 45 nanometers. So we'll revisit these images a little bit later and talk about what they looked like once the vibration problem was mitigated. And these problems extend not only into imaging and metrology, but they're also yield problems. So some of our biggest companies in the world like Samsung and Intel and TSMC, their yield is very, very highly tied to their ability to resolve images and do metrology operations quickly, as quickly and as efficiently as possible. So the price of our cell phones and the price of everything that we use has semiconductors that has semiconductors in it is all very tightly close to how well you can provide vibration control in semiconductor manufacturing, as an example. So we know we have a lot of high precision instruments out there, and we know it's a very big problem and an increasingly larger problem over time. Now we're going to ask ourselves, well, where does this problem come from? And the reality is floor vibration is everywhere. And it's most critical for microscopy in the 1 to 50 hertz range, but we'll talk about frequency of floor vibration a little bit later. And common causes are very often human activity. And it's human activity inside the building, people walking around the building, people riding the elevator up and down, somebody dropping their coffee mug on the floor. These are all sources of floor vibration. But we also have mechanical vibration from HVAC systems in this facility. We have motors and pumps and refrigerators. We have loading docks where trucks are rolling in and out. And then outside or underneath, you've got subways and traffic. All of these things are caused by our external vibration sources that can add vibration to your building and cause it to sway or bounce or vibrate or tilt or rotate. I'll talk about that later, in levels that are imperceptible to humans, but noticeable when you're talking about 5,000, 500,000 times, million times magnification. Nearby construction is also a very common one, where you might build a facility in a green field out where there's nothing nearby, and all of a sudden your neighbor builds a building right next door to you. So there's a lot of sources. And one of the key takeaways is your building can never be more quiet than the ground underneath. You know, you can build your building as massive and use all the tricks you can to mitigate vibration, but the vibration of the ground is critical. There's also vibration from natural sources, like what we've known as the microseismic peak, which is a very, very low frequency phenomenon that you can detect all over the world. And it's the collective sum of all the waves crashing on the shores, and if you all over the world. And if you have a sensor sensitive enough, you can measure this peak. Incidentally, the journal Science magazine started a study in 2020, July 2020, where they've noticed a notable decrease in cities due to less human activity due to COVID-19 lockdowns. So it was an interesting study because we were able to measure less people going to work and less traffic, and it was noticeable around the world. So if you're interested in the link to that study, please email me because I thought it was interesting. So it exists vertically and horizontally, and it can be introduced from all these different sources. And another source that people don't often think about is sometimes horizontal motion of the building can be translated into vertical motion. So a tall building swaying in the wind will create a torque on the corners of the walls and on the columns. And this torque will then create what we call a drumhead effect, which will then cause a standing wave in the building. So it comes from a lot of different sources, and it's sometimes hard to know where it exactly is coming from. And when you do a vibration measurement, sometimes your measurement includes some vector component of both horizontal and vertical motion. But a key takeaway is that it also can vary 1,000 times from location to location. Different floors will have different vibration levels. If you're near a wall or near a column versus in the center of a floor, you'll have different vibration. You can even have different places right next to each other where you might be at a node or a valley, because vibration is a standing wave effectively. And every standing wave is going to have a series of crests and valleys and nodes. And where you place your sensor is going to affect how you measure that. It also becomes complicated because there's a lot of different sources of things that you could also pick up when you're taking a vibration measurement, such as acoustic and barometric noise. So people talking and HVAC systems turning on and off in the system and in the facility where you have large movement of air due to a system due to a air conditioning motor kicking on, or even an elevator going through a shaft can send a pressure wave through a facility that's detectable and could be falsely identified as floor vibration. We also have systems that are meant to be isolated. So later on, I'll talk about mitigation systems, and your performance of that system is going to affect your vibration that you see when you take a measurement, if you're taking a measurement on an isolated surface. Instruments themselves generate noise. So a lot of the electron microscopes and other tools that we talked about, instruments that we talked about in the earlier slides, they're going to have some of their own pumps and motors and even mechanical arms and robotic components that might be generating their own noise. So you always got to watch out for noise that is generated from the instrument itself. And when you look at all these different sources of vibration that you might be picking up when all you really care about is floor vibration, the problem that you have to solve and the thing that you have to realize is that different vibration sources require different mitigation approaches. And today, we're going to talk again just about floor vibration. We're going to figure out how we're going to measure it and then how we're going to mitigate it. And as I mentioned before, floor vibration exists in 6 degrees of freedom. And this is because our tool is three-dimensional. An instrument that you might put on the ground that's vibrating is three-dimensional. And it might be partially on a node, might be partially on a crest, might be partially on a valley, and you're going to experience vertical vibration from that. You're going to experience left and right, maybe from building sway, and you might experience forward and backward. But then you're also going to experience combinations of these, where you're going to see pitch, roll, and yaw, where you're having combinations in the XZ plane or the YZ plane or the XY plane in the case of yaw. And this makes vibration a complicated problem to mitigate. Not only can it vary 1,000 times from location to location, but you also need to have a system that can provide 6 degrees of freedom for isolation. So we want to start to measure it now. And there's 2 types of sensors that are commercially available for measuring vibration. We have accelerometers, which are mostly piezo-based, and we have geophones, which are typically based on a solenoid. And an accelerometer is going to measure your signal. It's going to output a voltage or a signal proportional to the acceleration on the internal piezo. So when it's at rest, it's going to have a piezo, and that piezo is always going to be experiencing a force from the Earth's magnetic field, or I'm sorry, the Earth's gravitational field. And it's always going to be outputting a signal proportionate to that. Geophones, on the other hand, will have a output proportional to velocity. So some motion will then cause your inertial mass to run a coil over a magnet, which will then induce a current in that coil. And that current is going to be your signal that you're going to be reading. And there's different times when you use accelerometers and different times when you use geophones, but I don't want to talk about that too much in this presentation. So when we put our accelerometer on the ground, or we put our geophone on the ground and we decide to take a measurement, we might get a measurement that looks something like this in the time domain. So on the x-axis here, we're looking at seconds, and you can see that we took the measurement for roughly 16 seconds. And this is a geophone because I have an output in G's on my y-axis, and my amplitude is an amplitude in micro G's. And what we see here is something that looks rather noisy, and it's a combination of everything that is all the vibration that's being put into that the floor is experiencing. And it's hard to read. You know, the human eye is very good at picking up patterns, and if I was really feeling really ambitious, I'd go through this and kind of pick the peaks and maybe count that there might be 30 or 60 peaks in a 1 second period and identify that I might have a 60 hertz noise source or something like that. But there's a whole lot of other noise and a whole lot of information in this signal that I really want to know something about if I want to mitigate it. So what do? We use our spectrum analyzer, which is our standard tool for measuring floor vibration, and we have it do a fast Fourier transform on the signal. Our fast Fourier transform is going to resolve the signal as best it possibly can into the component frequencies. And its component frequencies then become something that we can start to talk about and start to say, well, what could these sources be? And we look at this and we see one very discrete, or I should say 3 very discrete peaks right about 60 hertz. And that's a very telltale sign of a motor running off of line voltage. So it could be an air conditioner that's turning on and off, and you might not see that all the time. Or it could be a refrigerator that's running all the time. Or it could be some other sort of, it could be somebody's fan. It could be a laptop fan nearby the place where you're taking a measurement. So, you know, it could definitely, but it's a very telltale sign of a high frequency, probably line voltage motor induced source. Probably won't be a laptop fan, incidentally, because those run on DC. But anyway, and then we look at the low frequency, and our fast Fourier transform has given us a little bit of information telling us, well, hey, there's a whole lot more noise going on at the low frequency. And we got to start thinking about those low frequencies, because those sources are going to be things like building sway, and those are going to be the real building vibration, that floor bouncing up and down at low frequencies that you really got to start thinking about when you're thinking about the instruments that you're using on this floor. And this chart is a little bit misleading because it shows that the 60 hertz problem is much higher than the low frequency problem, but in reality, it's really not that much higher. It's only 4 times higher. And I can slice and dice this a little bit more and use logarithmic plots on the y-axis and the x-axis, but I don't want to go too much into signal processing. I just wanted to point out that we got to do a fast Fourier transform on our noise source. We can try to start to identify what sources we're dealing with. And the next thing that's always true is that vibration increases over time. And here's a really great example of a study that was done by a consultant called Colin Gordon Associates. And they went into a semiconductor manufacturing facility that had just been built, and it was empty, and they took floor vibration measurements, and they got the red curve. And this red curve is very, very nice because we don't see too many, we don't see the influence of all the other things that could be a problem for this. And you see a very nice, say, 50 hertz peak, which is probably from some of the existing machinery and existing HVAC systems and things like that in the facility. But what happened was they went back about 14 months later and then 17 months later and took the same measurement and noticed but an order of magnitude increase at various frequencies, especially at low frequency, where we start to see the building being populated by people and by other equipment and things that are starting to introduce vibration. So the point is, you can never really rely on your vibration conditions always being the same over time. It's natural for it to increase, and it's always going to increase. And what makes this problem even more challenging is over time, you're going to want to be increasing your sensitivity to vibration because likely you're using a tool and you're advancing technology, and you're going to want to resolve smaller and smaller features. So vibration will, if it isn't a problem now, it probably will be in the future. And over time, we noticed this effect. You know, humans, engineers and architects and people that are building tools, you know, they started to realize they were sensitive to floor vibration. And we know floors can be noisy. And as our instruments increase in sensitivity, it becomes more and more of a concern. And so over time, things became quite haphazard. You know, architects would try to build buildings to specifications for floor vibration from instrument manufacturers. So for example, if I make a microscope and I want my customer to achieve a certain resolution on my microscope, I'm going to require my customer to provide an environment that has a certain vibration level. And I'll know what that is because I'll have tested it in my R&D efforts, and I'll tell them to achieve this level. And they'll go out to their architects and say, hey, we need this building with this level. And so you have all these companies and all these people coming up with different specifications and ways to meet the specifications. And it was a little bit like the Wild West until the early 80s, when Colin Gordon Associates again came up with what we call the VC curves, which is meant to be a common language for how we characterize floor vibration. And they selected different levels and sort of gave guidelines for what types of activities are good at these different vibration levels. And if you look at an office, for example, we're looking at vibration levels of roughly 400 microns per second, over a certain frequency range. And that's perceptible. Sometimes you can feel somebody walking in your office and you can feel a 400 micron per second velocity vibration. Even operating theaters, places where we're doing surgery and using some optical microscopes, that is on the vibration curves. But once we start getting down to really sensitive instruments, we start using A, B, VCA, vibration criterion A, B, C, D, E, F. And we get into the E, F, and G. This is where we're talking nowadays. We're seeing more and more instruments out there saying this instrument needs to be installed in a VCE, a VCF, or VCG environment, which are extremely difficult and very, 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 very high, I should say, very low levels of vibration in a facility. So we think we know where our vibration is coming from, and we think we've measured it and we've identified some of our vibration sources. And now we're going to talk about, well, how do we get rid of these? What do we use to mitigate our floor vibration if we want to install an ultra precision or a high resolution instrument? The first thing we look at is we'll look at isolators. An isolator is basically a fancy way of saying it's a spring. It's going to filter and it's going to provide a transmissibility function or a transfer function from what's input to the floor to what you measure on the payload. And that's very important because isolators are not meant to be something that can provide an absolute vibration level on a given surface, on the payload, I should say. What an isolator does is it provides an isolation factor. And so it's always a ratio of what's going in to what's going out. You always got to manage that when you're planning for your vibration control. And in our most simple passive isolators, like a damped mass on a spring, you have trade-offs. And you always have a resonant frequency if you're not using an active system. So what you see is sometimes a passive isolator will act as a rigid body and pass off frequencies, like a low frequencies here on this chart, where it's acting like a rigid body. Then the resonant frequency of that isolator is gonna peak. In this particular example, it's peaking at roughly 1 hertz. So what you're gonna see is amplification of any floor noise at that low frequency, which can become a bigger problem for any work that you're trying to do. And then you're gonna see a very fast roll off in a low frequency isolator where you have isolation at a much lower, at higher and higher frequencies. Take a step back. This chart is a transfer function chart, and the center line here is unity. So anything above the line is amplification, which is where I have my resonance, and anything below the line is isolation, where I'm providing some isolation factor by frequency. And if we have a problem with our resonant frequency, the first thing that we're going to try to do is we're going to try to introduce some sort of damping. And as we damp a system, we encounter trade-offs. What we can do is we can add some sort of viscous damping fluid or some sort of mechanical friction to the system, which we call damping, which results in a Q factor. And the problem that the more damping we introduce to a system, the less we may see our resonant frequency becoming a problem, but we're also going to have a trade-off at higher frequencies. So what this curve is meant to show is an example where we have a Q factor, a damping factor of 10, and it compares you to our difference in how much isolation we get. And you can see that there's a little bit of a trade-off. We have less isolation at higher frequencies. But say we get to a Q factor of 0.5, a very, very high level of damping. Well, we've done a pretty good job of almost mitigating our resonant frequency, but our high frequency isolation has suffered greatly. So there's always a trade-off. Commercially available passive isolators are oftentimes air isolators. So it's a sealed chamber that functions just like a mass on a spring. And what makes an air isolator or a pneumatic isolator unique is that it functions sort of like a barometer. It's a sealed chamber. And that sealed chamber is, you feed an air pressure into it and it floats a piston. And that piston floating on air is a very, very strong isolator at high frequencies. But it's also going to have it being a soft spring, it's also going to have a very, very strong resonant frequency at roughly 2 hertz. And air isolators do a very good job of isolating, and they're used in many of the precision tools that we've talked about in earlier slides. They're a little bit susceptible to changes in air, though, to changes in pressure, because as room pressure changes, this being a sealed air chamber, you're going to have the ideal gas law want to expand your air inside the isolator as the pressure in the room decreases, or vice versa. And as you have pressure changes in the rooms due to maybe doors opening or HVAC systems turning on and off, or an elevator going up and down a shaft, this could be a problem with a sealed air chamber design such as this. One thing that's really nice about commercially available passive isolators is that you can vary the air pressure inside it and therefore make it a little bit stiffer or make it a little bit less stiff. You can adjust its resonant frequency a little bit, but its resonant frequency is relatively irrespective of mass. And that's actually an important part about most isolators, especially if they're mechanical. So like a rubber isolator, something that's made out of a spring material, its resonant frequency is going to be very highly dependent on the mass that you place on it. But an air isolator, not so much, because you have the ability to vary that air pressure. And so an inherent factor of a characteristic of air isolators is this resonant frequency. And the resonant frequency at roughly 2 hertz is going to be something that could be very problematic, especially as you get into more and more sensitive instrumentation. And as you try to get things to higher resolution, higher magnification, an air isolator with its resonant frequency might not provide enough floor vibration isolation. So now we start talking about active vibration cancellation systems. And when we talk about active vibration cancellation systems, we're talking about something that has to have 3 critical components. The first is a motion sensor, the second is a force actuator, and the third is a control loop. And in its basis sense, what an active cancellation system is trying to do is it's trying to sense what the floor is doing, and then it's going to send a signal equal and opposite to its actuators to try to cancel out what it's feeling on the floor. And then we can take these components, we could divide them into 2 different types of systems and configure them in different ways. We have serial type systems and we have parallel type systems. I'm going to go in my next slides into a deeper dive into the different types of active systems that are out there that are and how they are used to cancel floor or other vibration. And we're going to start our discussion with parallel type active systems. In a parallel type active system, you have your 3 important components. You have your sensor, which is on your isolated payload. You have your feedback control system, which I have shown with this arrow. And then you have your force actuator. And a force actuator in an active type system is usually some sort of mechanical actuator that's oftentimes like a linear motor or a voice coil motor, something that has something that's a magnet coil type of force actuator. And an important takeaway is that these types of motors, voice coils, linear motors, they can't really bear the load of a system. They can only provide a corrective force. So you always have to have some sort of passive component in parallel with it. So you have a passive spring, and it could be a mechanical spring, a mechanical die spring, or it could be an air isolator, which is very common. And the key is your passive component and your force actuator act in the same plane on the payload. That's the basic construction of a system, of a parallel type system. And what are the ramifications of doing it this way? Well, there's several important things to consider. The first is that your sensor is on the payload. So when you're sensing a payload, as we talked about before, payloads can be inherently noisy. They have their own resonances. They have moving equipment and things on them. There's humans that are using them and maybe moving things on and off of them. They're susceptible to all sorts of external vibration. So your sensor is picking up all of that payload noise and feeding that and trying to cancel it out. At the same time, your sensor is sensing out any floor vibration that's coming in. So your floor is going to vibrate, it's going to translate and be amplified by the spring and be sensed by the sensor. So you're feeding a whole lot of information into the sensor. And your sensor doesn't know well, am I trying to cancel out floor vibration, or am I trying to cancel out payload vibration? So it tries to cancel everything. And when you do that, you start to encounter bandwidth issues. You can't really cancel just the floor if you're sensing payload motion and vice versa. So you've got to spread out your sensor bandwidth across a wide range of frequencies in order to try to cancel everything. And as you do that, you start to encounter stability issues. There's just too much information coming into the system. And what you need to do to try to get back some stability is start to detune the system. You start to say, okay, sensor, or OK feedback system, I'm going to make you less sensitive at some frequencies so I can achieve stability at other frequencies. And this constant balancing act. So what this makes it, what that happens is that makes parallel type systems notoriously difficult to get very good performance, especially at low frequencies, because many of the system, because your passive component is almost always going to have some low frequency component. And here's an example of a transmissibility curve you might see from a parallel type system, where at 1 Hertz, you've got some amplification due to the soft springs that are inherent in the system, but then you do get pretty good vibration isolation once you start to roll off at higher frequencies. But what's really happening here is it ends up looking more like a damped resonance with no trade-off at high frequencies, as opposed to something that's really providing isolation in a truly broadband sense. Because what you really want to see is you want to see isolation. You want to see this peak to be as close to 0 as possible. That's not to say that parallel type systems don't have uses. Parallel type systems can perform very well in on-board notion cancellation because they work very well and they're very, very open to what's called feed-forward capability. So we see a lot of parallel systems employed inside instruments that have a known motion profile. For example, a semiconductor manufacturing tool, which has got a stage moving back and forth, and we know the mass and the acceleration of that stage. So we can feed this information into our linear motor and start to have that motor react to a future force that we know is going to happen and provide really good onboard cancellation. And another type of active system is a serial type active system, which also includes the same types of components and an additional component. And they're also, the system architecture is sort of put together differently. I should also mention that these are one-dimensional three-body diagrams. Any system that's out there commercially is going to have this sort of theoretical construction in all 3 dimensions if it really wants to be a true active cancellation system. So in our serial type system, we have our passive spring. And our passive spring in a serial type system, the one that I'm going to be focusing on today, which is a piezo-based system, is going to be a stiffer spring. It'll be a rubber elastic isolator as opposed to something extremely soft like a pneumatic isolator. Our spring is supporting our payload. And then we introduce a new component we call the inner mass, which is going to be a very stiff, high frequency structure. And it's on this stiff, high frequency structure that we're going to place our sensor. And our sensor is going to then have our feedback loop, and it's going to feed back into our force actuators. And in this case, our force actuators are piezoelectric stacks. So a piezoelectric stack is going to be, it's roughly about the size of a roll of quarters. And it's a ceramic crystal that exhibits the reverse piezoelectric effect, which means when I apply a voltage to it, it's going to expand and contract proportionate to that voltage. And so what's also unique about using piezoelectric stacks in a configuration such as this is that your force actuator is also load bearing. Whereas in the parallel type system, our force actuator is not bearing the load of the system. It's the fact that we're using piezos, these stiff load bearing actuators, that allows us to do a serial type system and separate our actuator via the inner mass and our passive spring on top. So say a floor vibration comes in, and it's going to transmit through our force actuators, and then it's going to hit our sensor before it hits our payload. And then our sensor is going to do what a feedback system does. It's going to try to send back to the actuator an equal and opposite signal and cancel it out. And what makes this architecture especially unique is that our spring is isolating our payload. And our payload, as we said before, is going to have all sorts of noise on top of it. And all of that noise on the payload is going to be filtered out by the spring. So our isolator, our sensor is in a very large sense isolated by any of the noise on the payload. So we're freeing up our sensor to detect really only floor motion. And that enables you to provide much better performance in a broadband sense, especially at low frequencies, because you don't have all this extra information from the payload going into the sensor, and you're free to tune your system to really focus on low frequency floor vibration cancellation. Another advantage is that because we have this second stage of isolation in the passive spring, we can put any other isolation system on top of it, which I'll talk about in a later slide when I talk about combining isolation systems. These two have some of their own disadvantages. You know, it's a piezo-based system, which means we're going to have a very limited stroke. So if we start to get into a floor where you can feel the floor vibration physically, you probably don't have enough stroke in a piezo, because we're talking about micron displacements here that we're able to provide. But even at microns, as you guys saw before, these types of displacements can cause problems at the nano and micro level. Another thing they can't do is they can't cancel motion on the payload. But again, if you really want to cancel payload motion, there's systems for that. What we're trying to focus on here is floor vibration cancellation. And here's a typical curve of a piezo-based system transmissibility. And we've shifted our resonant frequency down way, way low. And what's so unique about this resonance is that it's not really due to the resonance of a soft mechanical component. It's due to simple tuning factors and filters of the system bandwidth, which I don't want to go into right now. But let's talk a little bit about the comparison between the two. And you can see the blue curve shows a serial type system where we have an extremely low frequency resonance and excellent cancellation once we start getting into 1 hertz and even down to 2 hertz versus our parallel type. Incidentally, we've never seen a problem from this resonance at such low frequencies. At a sub 1 hertz frequency, we're really talking about rigid body motion. And such a small amount, I've seen very, very few applications where such a low frequency resonance has actually become an issue. But what we're trying to achieve here with piezoelectric systems, we're trying to achieve as low resonance possible and as good a isolation factor as beyond that resonance, which we're achieving, as you can see in these curves. So what do our images look like once we apply a mitigation system? And these are all done using piezoelectric mitigation systems, serial type piezoelectric mitigation systems. And we have our image from before, where we had Portland State University with a problem with a train going by. And these are the vibration due to the train. And once we put this scope on top of our mitigation system, we limited that vibration. So this user no longer had to keep a train schedule next to their scanning electron microscope every time they wanted to do a measurement. We saw this again by mitigating these vibrational waves in this image at the Nationwide Children's Hospital in Columbus, clearing up the image to look like this. The scales that we're looking here are roughly 20 microns or so. I'm sorry, 200 nanometers in this length. And so once we zoom in roughly 10 times, we're looking at roughly 20 nanometer features. And here's another really good example from advanced immersion lithography. So we had a lithography system at CEMATEC. And at the time that they were doing this, it was the 2000s, and state-of-the-art lithography lines at that time were roughly 45 nanometers. Perform the operation trying to create this 45 nanometer test pattern where they're trying to get a gap of 45 nanometers between these two lines. You run the lithography equipment, you get the test pattern, you put it under a scanning electron microscope, and you see this mess. And once you isolate that system on a serial type piezo cancellation system, you run it again, you get this pattern, you put it on a scanning electron microscope, and this is the image that you get. And this is, again, a 45 nanometer image, which by today's standard in the semiconductor industry is actually quite coarse because, as I mentioned before, 5 and 3 nanometers are now the targets for our world-leading semiconductor manufacturers. So it kind of illustrates this coarse measurement how much even at this high, even at these high line widths, vibration was a problem 20 years ago. And a question that I always get asked is, well, can I stack my systems? Can I get my transmissibility? If I put one system on top of another, will I sum the transfer functions? And the answer is, well, usually you can, but you got to do it the right way. And you've got to achieve a certain type of, you got to achieve certain conditions. So you can go ahead and you can stack an active system on an active system, and you can put a passive system on an active system, which we do all the time when we put a scanning electron microscope with its own internal isolators on top of a piezoelectric serial type system. But we also have, but you also, even if you wanted to, put passive on passive systems. And you have to achieve one of two criteria to make this happen. Either a separation of mass or a separation of stiffness. When I talk about separation of mass, I'm talking about a large mass in between the two systems. So here's an example in a free body diagram of a relatively light system that has some spring constant, say the spring constant is K, placed on top of a very massive surface, also placed on a similar spring constant. So if it didn't have that mass there, those two springs would couple with each other. You get tilting effects, you get amplifications of the resonances, and you get all sorts of problems. But if we put a mass sufficiently large in between them, roughly 10 times is a rule of thumb, large, between the difference of the masses, then you can avoid some of that coupling, and you can get some transfer function summing. But be wary, because you may achieve stability, but you might not. But you're going to sum your transfer functions, but you're going to sum the bad parts as well as the good parts. So if you have a low frequency resonance in both springs, that resonance is going to get twice as bad. But the application at higher frequencies is going to get just as good. I shouldn't say twice as bad, but I say you're gonna have the sum of the resonance of the two springs, and then you're gonna have the sum of the isolation as well. So it works for some cases, but not always. Another way to do it is with separation of stiffness, where we achieve that in a serial type system. And what you do is you have your mass and your payload, and then you have that mass supported by some spring constant. Then you have a mass in between them, which is going to be necessary, but it's got to be some sort of platform or some sort of interfacing surface. And then you're going to have a spring with a much higher spring constant or a much stiffer spring. And that stiffer spring will be much less likely to interact with a softer spring on top of it. So by achieving a separation of stiffness, which we call an impedance mismatch, you can effectively stack two systems of similar stiffnesses. And this is one of the reasons why you can stack serial type systems very effectively, because a serial type system uses a piezoelectric, which is a high stiffness component. It's going to use a rubber mount, which is going to be a high frequency component. And if you put something on top of it, like an air isolation system, which has a low frequency component, you have that impedance mismatch. And we do that oftentimes in a product we make called the TMC Stasis Laser Table Base, where we have a series of air isolators, which have a low frequency resonance, stacked on top of a piezoelectric cancellation system. And we have the separation of stiffness, and we get a really nice summing of the transfer functions where we can achieve both high frequency cancellation and low frequency cancellation. The low frequency given to you by the piezoelectric components, and the high frequency given to you by the passive air isolation components. So we're almost at the end of the presentation, and I'd just like to conclude with a statement that as technology advances, the need for ultra-precision instrumentation will also increase. And vibration, as a result, will also become an issue. So it's important to think about your floor vibration sources, to measure it, to characterize it, and choose the right mitigation systems to help you achieve what you're trying to achieve with your ultra precision instrument. We're going to open it up to questions now. And I'd like to invite you, before we do that, I'd like to invite you to message me if you have any questions or suggestions for topics for future webinars. You know, we at TMC, we're a world leader of understanding ultra precision instruments. We have a manufacturing facility here at the U.S. Just in the U.S. Just north of Boston, where we basically spend all of our time thinking about floor vibration, magnetic fields, and issues. And so we have a lot of expertise in how to prevent vibration, where we have a course that's actually AIA accredited. We talk about control systems. We can talk about vibration measurement, acoustics. We can talk about magnetic fields. We can go into deeper dives on vibration control systems, like I talked about earlier. I had some allusions to some stuff that I really couldn't get into too much detail. But if you'd like a more detailed talk on any of these, please feel free to message me. And with that, I'd like to thank you all for joining. And I'll turn it back to John, who will answer any questions that may have come up throughout the presentation.
Oh, thanks, Mike. That was terrific. Yeah, we do have a number of questions, and you bring up a good point. Maybe we should send out a survey to the group and ask, what they'd be interested in. But yeah, we have I don't know, about 10 minutes here. So first question, Mike. Many thanks for the nice presentation. Between vertical and horizontal vibrations, which source typically has a higher amplitude?
Wow, that's a great question. Thank you. And there's really no way to say which one's more typical, because every vibration condition is different. And if you think about where you are in your building, you can have different floor vibration problems. Like, for example, in a high floor, in a tall, narrow building that's swaying in the wind, you're going to see very likely a low frequency horizontal influence. But they go down to the basement of that building, you might see no horizontal, but the building sway above might generate that drumhead effect that I was talking about, and you might see a strong vertical issue due to the horizontal sway of the building. So a lot of that has to do with building construction and where you're located in the building. So I'm sorry, there's really no good way to say which one's often higher amplitude. But thank you for your question.
Okay.
I hope I answered.
Yeah, so we need to measure. Next one, I do atomic force microscopy. When I do control measurements of vibration systems into my system, I notice that there are vibrations at higher frequencies, higher than 200 hertz, somewhere around 500 to 1,000 hertz. What can be possible sources of vibration above 200 hertz? Can there be mechanical vibrations above 200 hertz?
Yeah, mechanical vibrations can exist at 200 hertz, but what we see at those really high frequencies are extremely short waves. And those short waves in a floor just don't have that much energy to really induce it into your scope. So what you're really actually probably seeing, is my guess, is probably something acoustic. 200, 500, I mean, 500, you're starting to get into a range of audible sound. So actually audible starts around 80 hertz. So I would actually start to take a look around your facility and maybe look for things that you can hear that are introducing that vibration, because at that high frequency, it's not likely to be coming something from the floor. I think you're seeing an acoustic effect. Good question.
Another one. What is the typical mass ratio between the inner mass and the mass to be isolated for a serial type active isolator?
That's a great question. The inner mass is actually in commercially available systems, you don't need very much mass at all in your inner mass. The key to that inner mass is a high frequency structure. So an inner mass only needs to be a few kilograms, and then on top of the system you could put several thousand pounds, because really the key to the inner mass is just a surface to provide a high frequency separation and rest your sensor on. It's really not something that needs to be there. Its mass is really not critical to provide a coupling of anything that's above it.
Okay, thanks.
I should say decoupling, I'm sorry, decoupling from anything that's above it.
Let's see. What if the vibration coming from external sources is not steady or not constant? How would we handle that?
So that's an interesting one. What you're talking about is non-stationary noise. You know, it's something that happens once in a while, and you might not even know when it's going to happen. So it could be maybe truck deliveries in a facility. You know, it's worse than an HVAC system which turns on fairly regularly, or it's worse than traffic outside, which you know when rush hour is going to happen. So you would still use the same mitigation sources to cancel out non-stationary noise. The trick to non-stationary noise is capturing it. You know, if you think you have a vibration that occurs every night at say 4 a.m. and you see that, you know, in your measurement, you know, you've run a measurement overnight and you see that there's a disturbance at 4 a.m. You might want to start looking into, well, what's happening at 4 a.m. that's causing that vibration? And it could be something as simple as, you know, a cleaner moving, you know, moving some equipment that happens every night there and things like that. So I guess in conclusion, I would say any mitigation system should be able to do, it's going to provide a transfer function. And if you are lucky enough to to be able to measure your non-stationary noise, then you can then think about a mitigation system that will provide enough attenuation for it. And when you don't have that, well, that's great. You have even more vibration, even less vibration on your surface. And when you do have that non-stationary noise, well, hopefully your system's providing enough attenuation.
Okay. Next one, what device is typically used for characterizing, measuring vibration on small surfaces, like on a microscope stage?
I guess that depends on the what you have available to you. You can use either a geophone or an accelerometer. It depends on the equipment that you have. I'd say that if I were to try to figure out what type of vibration I have in my microscope stage, I'd probably use an accelerometer because they're very well commercially available. They've got great calibration standards. There's a lot of support out there from third-party companies that design software and analyzers that support accelerometers. I think you just have an easier time trying to measure that if you went out and found you know, somebody that provides an accelerometer. We at TMC, we use an accelerometer from Wilcoxon. That's a really nice one. And we use a spectrum analyzer from a company called Data Physics.
Okay, thanks. Assuming a similar size isolated pad, on a rough order of magnitude, how much more expensive is a serial system versus a parallel system?
You know, if you're using a large isolated pad, that's a hard one to say because a large isolated pad, you know, if you're using a big concrete block and you're supporting it with one active system or another, you're going to be looking at not too much of a cost differential, you know, because and it depends on the size of the pad. It also depends on what you're trying to achieve from floor vibration isolation. And you know, with serial type systems, you might even have the option of eliminating the pad, which could then significantly lower the cost of the system. So it depends on a lot of things, but I would say if you're trying to cancel floor vibration, you know, if your concern is floor vibration, then you're going to want as much bandwidth as possible for cancellation, and so you're going to want to go with a serial type system because that's going to give you the performance that you really need.
Okay, thanks. Thinking about high resolution optical microscopy and microscopes, is it typically floor vibrations or acoustics of the room that affects the imaging performance most?
Yeah, it's similar to the atomic force microscopy question we had earlier. And it could be one or the other. It just depends on the facility and what your problems are. A lot of optical microscope setups go on passive isolation tables. And those passive isolation tables are going to do a great job at high frequency floor vibration mitigation, but they're going to have a resonant peak at 1 or 2 hertz, which could be giving you a problem due to building sway. But you're always going to have acoustics in your facility due to whatever sources. So really the best way to try to figure out where your problem's coming from is take a measurement of the floor and take a measurement of your surface and try to start to point out you know, what exists on the floor that might what exists on the surface that might not exist on the floor. And you might be able to identify some system resonances that way. So it's a complicated problem to solve and identify what's causing your issue. And I really don't know enough about optical microscope construction itself to say, definitively whether it's acoustics or floor vibration. I think each system's going to have its own frame. Each system's going to have its own resonances. I think that they're all going to be kind of have their own, sort of weaknesses.
Yeah. Okay, we're running up on time here. I'm going to give you one more question, Mike.
Okay.
And just to the people whose questions we haven't answered, we will get back to you with answers. So last one, following the question on instantaneous vibration sources, what are the differences in reaction time for serial versus parallel systems?
That's a complicated question to answer because it depends very much on the design of the system. But I think one of the things that I think is key between the two systems is the frequency of the components that are bearing the load. So in a parallel type system, you've got a fairly low frequency source that's bearing the load of the system. And as you get a disturbance in, it's going to take some time to travel through that low frequency support and then get sensed by the velocity sensor or the accelerometer and then get canceled out. Whereas in a serial type system that's based on piezos, your piezos are crystalline rigid structures with a very, very high resonant frequency. So a disturbance may take a very fast time to reach out to go through those and then get sensed by the sensor on the inner mass, which the inner mass is also very high frequency, and then get sensed out. So I'd have to say in general, a piezo-based stiff serial type system is going to have a faster reaction time, and that's one of the reasons why it's got a better broadband cancellation factor. That's also I don't want to digress too much, but that's the answer to your question.
Okay, thanks, Mike. Yeah, so we're out of time here. We're going to end it. If you want to contact Mike, his contact information is up there on the screen. And also, you can go to our website, fill out our contact us form. So thanks very much for attending. We appreciate your interest.
Thank you, everybody, and have a great day, evening, afternoon.